I need to record that. Okay, good. So a sequence of the vectors here, and so we are going to define the convergence. So you have already learned the number here, the number limit in the calculus class, right? If you have x n and then the let's say the x, let's say, okay, this is the 0, 1, and then this is a sequence of the number, and then it's starting from 0 0.1, 0 0.1 square, and then you take the n takes to the infinity, and then this one is equals to 0, right? And this is the limit in the real number. And then now we have the limit in the Rn, the n-dimensional space. And then so let's see what happens. So let's see what happens. We have a sequence of vectors, and then in the n-dimensional space, and then it's set to converge to the vector x. Vector x. With respect to, I'm going to use the shortcut here, and then this shortcut is with respect to sorry, I need to go down this chain of these things. Thank you. Okay, and then it says this sequence of the vectors is converging to this vector x with respect to the norm here. So you can see the norm is very important here. It's a measure of the distance. And then if you take different norm, and then it would have different convergence results. And we say the sequence of the vectors is converging to x with respect to the norm. And if this is quite similar to the limit definitions in your calculus class. Given any epsilon, so we have the epsilon and epsilon's definition here. Given any small epsilons bigger than 0, there is says the an integer related to the epsilon we choose, and then this integer such that the x k minus the x, that is the distance between the x and the xk's we choose here, and then it's smaller than the norm of this one. The norm of this one, it means that the distance between these two vectors, right? So the distance between these two vectors is smaller than the epsilon. This is any epsilon we choose here. It's smaller than the epsilons for all the k is bigger than the n epsilons, this integer. And this is quite similar to the definitions of the limit in the calculus. But here we have just the Rn space, the n-dimensional space, and then we use the instead of the absolute value in the definitions in the calculus, and then we have the norm here. We don't have the absolute value, we have the norm here. The norm of the distance, the norm of this vectors here, and this represents the distance between the vector k and then the x. And then it means that there, if given any small epsilon value, and then there is an integer, and then for the k, which is bigger than this designated integer, and then we have the distance between these two vectors is smaller than the given arbitrary small epsilon here. And this is the definitions of the limit of the convergence in the Rn. So that's all the things about the vector. Any question here? Convergent definition is really important to understand the material. Any questions? Okay, if you don't have any questions, then let's go back go to the next part. The next part is about the matrix norm, and then the matrix norm and matrix distance. Here we have defined the vector norm and then vector's distance and then the vector convergence here. And then the next part, we are going to define the matrix norms here. Matrix norms and distance. Actually, we are going to use the definition of the vector norm to define the matrix norms. And first, we need a definition of the matrix norms, and then that is say things the same procedures as we did here for the vector norm. Definitions, and then about the matrix norm. And it has several properties to satisfy. And then the matrix norm, so I'm going to say, okay, this is a function. It's a function. I'm going to also use a double bar here to denote the function. And then it's mapping the n by n matrix to the real value, the real number sets. And then that's the matrix norm is a function. It's mapping the n by n matrices set and then to the real number. It should satisfying the following properties. Following properties, we have more properties than the vector norm here. So we have 1, 2, 3, 4, 5. We have 5 properties. 1, 2, 3, 4, 5. And then the first one is due non-negativity. And the second one, and then it's also the definites. And then the third one is also the homogeneity. And then the fourth one is also the triangles inequality. So let me write down the definitions on the right hand side. So the negativity, it means that for any matrix A, you have, it should be bigger than or equals to 0. So it should satisfy the following properties for all matrix, for all n by n matrices A and B. So for any A matrix, n by n matrix, and then it should be have the function of the A, it should be the negative and then definite. And then it means that if the function or the norm of the A equals to 0, and then if and only if the A is the 0 matrix. 0 matrix, it means that it has its entries are all zeros. So this is the definite. And then what is the homogeneity? Homogeneity, it means, okay, I need to write more things about the preset here. So it satisfies the following properties for all the n by n matrices A and B, and also for all the alpha in the real number set. And so for the homogeneity, and then if we times the matrix with the coefficients R bar, and then take the norm, and then it's just equals to the R4 absolute value, and then times the original matrix norm A. The fourth one is your triangle inequality, and then it should be, so the sum of two matrices, and then take the norm, it should be smaller than or equals to the norm of this, the sum of the norm. And there's one more thing. So we have some similar things in the vector norms definitions, right? We have the non-negative, definite, homogeneity, and then triangle inequality. We have the similar things, and but here we need one more things to be a matrix norm, and it's the inequality about the products of the matrix. So we have the product of the matrix here, and then we want to take the norm of that. and then it should satisfy the, it should be smaller than or equals to the product of the norm. So these are the matrix norm properties it should satisfy. And if you are given a function, and then on the n by n matrix part, n by n matrix set, and then it's mapping the n by n matrix set to the real number, and then you want to check if this function is a matrix norm, and then you need to go over all these 5 properties here, and then to see whether it satisfies these 5 properties. If it satisfies all of these 5 properties, and then we can say this is the matrix norms. So I'm going to give you one theorem here, and so before we move on, and so once you have the matrix norm, and then you can also define the distance of the distance between 2 matrices, right? So distance between 2 matrices is also, it can also define in this way: distance between 2 matrices matrices, and so it's just the norm of the subtractions of 2 matrices, and this is the distance between 2 matrices. And so here I'm going to give you some conventional norms here. So there's one theorem here. I'm not going to prove the theorem, and then but this one should be on the textbooks I show you before. There are 2 textbooks we are using, and then I'm going to use in this part I'm using the second textbook, and this is the theorem 1, and it's telling us how to calculate the matrix norm. So if this one is the vector norm, so we can calculate the matrix norm with the so we can define a matrix norm by the vector norm, and then so here this is the vector norm on the n-dimensional space. Then we can define the matrix norm in this way. So it's the maximum of the AX, and then X equals to, this is the unique vector. Unique vector, it means that the vector norm is equal to 1. And then we are taking the maximums among it, and then to define this function. So this is just the definition of the functions on the matrix, n by n matrix, right? And then if you want to check it, and then check the property 1, 2, 3, 4, 5 there. And then you can check this function taking the maximums of this vector norm here, and then it should be, it's a matrix norm. So here there are 2 norms here, and then this is the vector norm. And then this is the matrix norm defined here. And then this is still a vector norm. And this is still a vector norm. Does it make sense? So it means that, okay, so you have a bunch of X vector in the Rn, right? And then you use the A matrix to do some transformation. This is the A matrix, right? And then you have the X vector, and then you have the A matrix here, and then you get the AX. And then what is the AX? A times X. Is it a matrix or a vector? Vector. Because it should be the n by n matrix, right? Times the n by 1 vector. And then so this one should be an n by 1 vector, right? So after you have the X vectors from the n-dimensional space, and then after some transformation, the A transformations, and then you get the AX vector, n by 1 vector. And then you take the norm, and then you take the norm, and then compare all the results you have, and then take the maximum. So here we just evaluate the norm evaluate all the vector norms that are the unit vectors, and then take the maximum among it. And then this is the bigger value, the biggest values of the AX. And then that is how we define this A matrix norm. And then if you check this maximums expressions here, and then check that property 1, property T2, that is the negative, definite, and the triangle in coordinate, so on and so forth, the phi property there. And then this definition specifies that those 5 properties, and then we can say, okay, this is a matrix norm. And this is the theorem 1, and I'm going to skip the proof here, but you can go back to check the definitions one by one, and then to make sure that to confirm that, okay, this is a matrix form. But now I'm going to tell you some things that actually you can have. So I'm going to give you 2 definitions here first. So you can see that we can define the functions, right? A infinity. So from this theorems, 1, and then if we want to, we can define the infinity norm of the matrix by taking the maximum of among the unit vector, and then AX, and then take the infinity norm. And this is the vector norm on the right-hand side, but this is how we define the matrix infinity norm. And then, so we also have the Elder norm for the vector, right? So here we have the Elder norm for the matrix. And then we are taking the maximums among all the vector, the unit vector, and then taking the AX, and then the L2 norm here, the vector norm. So we are taking maximums among all the unit vector and on the right-hand side. And then that is the definitions of the L2 norm for the matrix norm. And so here we have such a things here, but actually we are not going to use C. You can see that there are infinite unit vectors in the Rn, right? Infinite one. So if you take the maximum, and that's a problem. You cannot take the maximum because you need to take all the vectors in the Rn, and then that's impossible. But there are some theorems to help us to calculate such infinity norm and 2 norm here. And I'm going to just state the theorem, and then we are going to use that theorems to calculate the A infinity norm and A2 norm. So first, I'm going to give you the definition, the theorem below. Theorems 2, let's say this is theorem 2, and then so A is an n by n matrix, and with the component its entry is Aij. Then the L infinity norm could be calculated in this formula, taking the maximum 1 smaller than I, and then it's between the 1 to n, and sigma sum and j equals to 1, and then Aij. So what does it mean? So it's doing the sum regarding the J index, right? And it means that we are doing the sum of the absolute values for each row, and then taking the maximums of this sum among all the rows. And then that's our A infinity norm. And I'm going to memorize this theorem in this way. So infinity, right, is in these directions. And then so we are going to do the sum in this direction, and that's the row. So you can just look at the infinity, and then that's the row. And then we are going to take the sum of the row, and then take the maximums among all the rows. And this is how I memorize it. Next, I'm going to show you one example how to calculate the infinity norm with this theorem. So one example here to calculate the infinity norm. So let's see, A equals this matrix 1 to -1, 0, 3, -1, 5, -1, 1, this one. So before I mention how to calculate it, and then I need to also tell you why we are learning the matrix norm, right? I know a lot of students say, you tell me to learn these things, and then, but why? So here I mentioned why we need to learn the matrix norm. That is because I just say the black box, right? The black box, we have the matrix there. And then we are doing some integration here, right? And then sometimes this method doesn't work, and then sometimes this method works. And then we have some criterions, some pre-check there to check whether this system work. And that pre-check things is related to the norm of the matrix. So now we are learning the norm of matrix because we can check whether that matrix can use such an iterations methods. And that's why we are learning the matrix norm. So let's go back to that one examples. And then later on, you are going to use this matrix norm to determine whether we can use the iterations methods. So let's see how to calculate the A infinity norm here. So solutions. So we are going to row by row. So let's see. For the row 1, we have, which means that the I equals 1, row 1, and then which means that I equals 1. And then we are going to do the sum for that row, the sum of the absolute value, 1, sigma sum j equals to 1, 3, and then A1j. And this is the first row, and which means that it's the 1 absolute value, 2 absolute value, plus the -1 absolute value, and then it equals to, it is just the absolute value of the first row, and then we do the sum, and it equals to 4. And then the second row, row 2, and then I equals to 2, and then we have the sigma sums for all the second row element, taking this absolute value, and then taking the sigma sum, we have the 0 plus 3 plus the -1, and taking all the absolute value here, and it's equals to the 4. And for the row 3, and then now this one is I equals to 3, and we do the sigma sum, and it's just the third row, all the elements in the third row, and then it's just this 5 plus -1 plus the 1, and then it's just the step 1. And now we are going to use that theorem we just mentioned in the theorem 2. So the A infinity norm, it should be taking the maximums among the result here, among all this row result here. So it should be, so from the theorem 2, we know that A infinity norm, it should be the maximums among all this result is 4, 4, 7. The result we have on the right hand side, and then the maximum, and then the infinity norm is just 7. Any question how to calculate this infinite norm?
So what if we had the matrix 5, 0, 0, 5, 0, 0, 5, 0, 0, right? Okay, never mind. Sorry, I just answered my own question.
You get it, right?
Yeah.
Okay, 5, 0, 0, 5, 0, 0, 5, 0, 0, and that is 5, 5, 5. And taking the maximum is just 5. Any other questions? But remember that you need to be very careful every time you need to take the absolute value. Question? No questions. And so let's see. I'm going to talk about, I'm going to move this part later. And it's interesting, but later I will mention this. And let's go to calculate the Altaron norm. Do I mention the spectral? I should mention the spectral first. So before we calculate the L2 norm, I'm going to introduce one more thing. It's the spectral radius. And the spectral radius is helping us also calculating the L2 norm. And then also the spectral radius of a matrix is helping you to determine whether this system's the iteration method worked. So here I am going to, the next part, I'm going to introduce the spectral radius of the matrix of a matrix. And this is the next part. And okay, so before I give you the spectral radius definitions, and let me see. The definitions, I need to mention something about the eigenvalue and eigen function eigenvectors first, because we are going to use the eigenvalue to define the spectral radius of matrix. So definitions is the characteristic polynomial. This is the definitions about the characteristics polynomial of a matrix. So if we have the A is n by n matrix, then the characteristic polynomial of A is defined in this way. It's defined. So it's just the P and then lambda, because it's the polynomial, right? And then it's a polynomial, it's a function of lambda. And then how we define this characteristic polynomial is just the determinant of the A subtract the lambda and then times the identity matrix. And that's the characteristics polynomial. So let me give you one example and how to get the, let me see. I will give you the examples later because we are going to calculate the spectral radius with the definition of the characteristic polynomial. So let's see, the next definition is about the eigenvalue and eigenfunctions and eigenvectors of a matrix A. And this is the second definition here, eigenvalues and eigenvectors. So it's related to the definitions we have here, the characteristics polynomial. If the P is the P lambda is the characteristic polynomial of A, then the zeros, it means the roots, the zeros of the P, this is P lambda, the characteristic polynomial, the zeros of the characteristic polynomials are eigenvalues. We call they are eigenvalues. So this is the definitions of eigenvalues, the zeros of the characteristics polynomials of A. And what about the eigenvectors? Eigenvectors, it's related to the eigenvalues. If lambda is an eigenvalue of A, and we have a non-zero vector, satisfies the A minus lambda I, and then times the X equals to 0. So we calculate the eigenvalue first, and then once we get the eigenvalues, we can check whether to find out the eigenvectors, the non-zero eigenvectors corresponding to this eigenvalue, and then that satisfies this equation: A minus lambda I times the X equals 0. And we require that this vector here to be non-zero vector. to be eigenvectors. So if it satisfies such an requirement, then we call X is an eigenvectors. Corresponding to eigenvector of A corresponding to the eigenvalue lambda. So in this class, I'm not going to tell you how to calculate the eigenvectors, but I will just focus on the eigenvalue part. But if you are interested in how to get the eigenvectors, you can go back to take a look at the textbooks for all the details. So I'm going to use the eigenvalue here. So don't forget our original goal. We are going to define the spectral radius. We go from the characteristic polynomial. We use the characteristic polynomial to define the eigenvalues and eigenvectors. And then now we are going to use the eigenvalues to define our ultimate goal. That is the spectral radius. Definitions. And then that is the spectral radius of A. And this is super easy. And then we use this notation here to denote the spectral radius. Spectral radius, we use the rho, not the P. This is the rho. P, it looks like this. There's one small tail here, and then that's the P, right? But here, there's no small tail here. This is the rho. And we use the rho to define the to be the notation of the spectral radius. Spectral radius rho A of A. So spectral radius of A, and then it's defined in this way. Rho A, it is just the maximums of the eigenvalues among the eigenvalues, and then where the lambda is in eigenvalue of A. So this means that we are going to take the maximums of all the eigenvalues of A. So I need to tell you that if the A is a real matrix, and then you have like n by n matrix, and then you will have n eigenvalues. So here, if A is an n by n matrix, actually you are taking maximums among n values. Does it make sense? If it doesn't make sense, let's take a look at one concrete examples. But here, the lambda could be a real number, and then it could be complex number. So if it is a complex numbers, and then what's the absolute value side here? It is not the absolute value. It is the so here for the if this one is a complex number equals to alpha beta I, and then we define the lambda, this norm of the complex number, and then it's just the alpha square plus the beta square, and then taking the square root. And this is the case when we have the complex numbers in the eigenvalues. That's for the spectral radius definitions. So now we have already defined a lot of things, right? And then a characteristic polynomial, eigenvalue, and then spectral radius. So let's see one concrete example how to calculate the spectral radius of a matrix. So I'm giving you one concrete example here, and then it's the examples A equals to this matrix 2, 0, 0, 1, 1, 2, 1, -1, 4. So as we see here, we have 3 steps, right? First, we need to define the characteristics polynomial. So the solution, first step, characteristic polynomial. The characteristic polynomial of A is this. It's the P lambda equals to let's go back to what we have in the definition, the determinant of the A minus lambda I. So what does it mean? It's just the determinant. So what is the concrete expressions for that matrix? It's the A subtract the lambda I. Lambda I is the lambda times the identity matrix, right? And it's just the, on the diagonal, all the diagonal elements are lambda, and then all the things out of it are zero here, zero here. So if we use the A, subtract the lambda I, and then it equals to 2 subtract lambda, 0, 0, 1, 1 subtract lambda, 2, 1, -1, 4 subtract lambda. And you need to use the definition of the determinant here to calculate the determinant. So we can expand around the first row for the determinant, and then that should be the 2 minus lambda. Let me see, am I right here? 2 minus lambda, and then times the determinant of the submatrix here. And then this one, it should be 1 minus lambda, 4 minus lambda, subtract the 2 times -1. And then that's it. And that's the determinant, because we can add the rest of the things, and then that is 0. And then there's 1 coefficient in front of it, -1 to the 1 plus 2, but it doesn't matter because this is 0 and this is 0. So after all the expansions of the determinant, it should be just the first one, 2 minus lambda, and then the determinant of the symmetrics here. So after some factorization, I'm going to skip this factorization part. I would leave that as a homework, or you can go back to check the factorizations here. So after some factorizations, you would have, so here, if you just expand it out first, and then you would have this equals to the negative lambda cubic lambda 7 lambda squared, and then 16 lambda minus 12. And then if you do the factorizations for this one, and then you would get negative lambda minus 3 lambda minus 2 and then square. So actually, if you have a calculator, maybe you don't need to calculate it by hand, and then you just need to put this into the calculator, and then ask the calculator to solve the lambda for you. You can do this. You don't need to just calculate it by hand. But here, after some factorizations, and then it's very obvious that, so now what we are going to do, we get the characteristic polynomial, right? And then we want to get the zeros of the characteristic polynomial, and then that are the definition of the eigenvalues. So there are 2 eigenvalues here, because if we let this one to be 0, and then we solve for the lambda, and then we got lambda equals to lambda 1, this is the first eigenvalue, and lambda 2 is the second eigenvalue. And this is a step 2. So for the lambda, get the series of the polynomials here. And then this is the second step, we get the eigenvalues. And then what about the third step? So the spectral radius of A is just a row A, and then taking the maximums among all the lambda we have, and which means that we are taking the maximum among 3 and 2, and it's just 3. And that's all the things we have here. We are preparing for the next class, and then we learn a lot of the lumps here, lumps of vector, lumps of matrix here, and then you will get practice on the definitions later on in the homework. Thank you. If you have any questions, and then you can come over here.
就是 homework， 然后这方面我们设计的定义这个说它是属于 real 的，
是
然后他就只是说这个是要，他就是要
Positive
positive，
对
但是也不能为。
对。
然后这个是不是第一个就是已经不是dominant diagonally dominant
对，
啊？
就六小七嘛。
对，因为我跟别人对答案的时候就感觉OK，那应该就没有什么了。
对，挺好的。
然后positive definitely 可以这么
可以，就是我那个也有给 example，
对
然后这是
我看了
preferred，
所以就是这两个
两个
都是
都是方法
example，然后只有这些是题。
对，只是这么
哦
小的，对对。
So I just had a question on number 2. So this one, since it's not diagonally
Yeah,
dominant,
yeah.
sounds fine.
Yeah.
But I just had a question on Cholesky's factorization. Like, what's the end goal with it? Because I know with like the LU, you get like what S equals, or at least like in this case, you get like your X values. So I understand that, but like with this one, it's just like you kind of break it up unless I did.
Oh, this one is just the factorizations, and then I am not asking you. This is problem 2, right?
Mhm.
And then I'm not like asking you to solve for linear system of equations. Actually, you can if I have so could I write it? Let me see. There's still some space here.
Mhm.
So in the question 1, I asked you to do the LU factorization and solve the system of equations with the LU factorization, right?
Mhm.
And then for this one, I don't ask you to do that, but actually people use this Cholesky's factorization to solve the linear system equations. Once the people get this B transpose, right?
Mhm.
And then they will solve, this is the original equation, right? X equals to B.
Mhm.
And then now they have BB transpose X equals to B. If the B is given, and then you can solve for the X, right?
Mm, since you
Any-
don't have B given.
Any B, right?
Okay,
and
so you
then-
just end up with this.
Yeah, and
Okay.
but this is the end of the solution
Mm,
because
okay.
I don't ask you to solve any X.
Okay,
Yeah.
that makes sense.
Mm.
Because I ended up with the same thing at the end, like plugging it back in. I was like, oh, okay.
Yeah. Because you this is the end of the solution because
Okay.
this is just the factorizations.
Okay, cool. Thank you so much.